Hello, everyone, and welcome to our Digital Life, a podcast series by IEEE Signal Processing Society. Founded as IEEE's first society in 1948, the Signal Processing Society is the world's premier association for signal processing engineers and industry professionals. In this series, we'll have candid discussions about developments of various areas of signal processing, which are the underlying ubiquitous technologies for today's modern society. In today's episode, we'll be discussing various advancements of AI and ML in signal processing techniques with our guest, Professor Sergios. My name is Dennis, your host.
First of all, I would like to thank you for the kind invitation. My name is Sergios Theodoridis. I'm Greek, as you realize for my name, and I am Professor Emeritus for Signal Processing and Machine Learning with Department of Informatics and Communications of the National Kapodistrian University of Athens. I'm also adjunct professor with Aalborg University, Denmark, and I'm also affiliated with the Research Institute for Big Data with the Chinese University of Hong Kong at Shenzhen and China. So that's my affiliation, and I've been involved with signal processing and machine learning for a number of decades now. So I have covered various topics in the signal processing and more recently of what we call machine learning.
Thank you. That is a concise introduction. I know you have more accomplishments. So to kick it off, Sergios, could you share a brief overview of your journey into signal processing, and particularly what inspired you to get into this field?
Yes, as a matter of fact, my first degree is on physics. And during my undergraduate studies, my favorite topics were mathematics and theoretical physics. And I still recall with some of the colleagues, we had created we have formed the so-called theory club. Sometimes we used to call it, where we used to get together and try to solve problems, mathematics, and discuss various topics on theoretical physics. Pretty naive. We were kids at that time, but that was interesting, questions related to quantum mechanics, relativity, and black holes. So for me, that time, it was just pretty obvious that the only decision I would take for carrying on postgraduate studies was to study theoretical physics. For me, there was no other choice. During my final year, I was applying to various universities for postgraduate master's degree. And then I looked at a book by Norbert Wiener called Cybernetics. Well, I said, that's interesting. Then I bought the book and I glanced through, and that was a revelation for me, because for the first time I came across concepts like information, communication, and control. And above all, I was impressed that these concepts have a commonality between machines and living organisms. So that really grasped my mind and excited my imagination. So I thought, let me learn a bit more on that. So I changed my focus and I tried to find a course that was related to these topics. Of course, at that time, there were not any AI or machine learning courses. They were just spread in computer science, which not many computer science departments at that time anyway, and electrical engineering. And then suddenly I found a course with the name Information, Communication, and Control. Well, that was it. So I applied, I was accepted. So among the obvious courses, formation theory and communications and antennas, propagation, which they were topics that I could handle because, I knew the tools from physics, electromagnetics. There was a topic which I've never heard of it before. The title was Stochastic Signal Processing. And the book, it was Laffy's book. If I recall well, it's random processing or random signals or something like that. I don't remember the exact title. One of the best books I've ever read. So, that was it. I fell in love with the topic. I said, but that's exactly what I want to do. So that's the beginning. In my PhD, I was involved with adaptive algorithms. These days, we call them online learning algorithms. At that time, we used to call them adaptive algorithms for stochastic signals, radar stochastic signals using autoregressive models and autoregressive moving average models. So that's it. I mean, this is basically the line that I followed, or maybe the line that followed my career throughout all these years. I started with linear models, then I moved to nonlinear models, polynomial extensions, Volterra filters, then the reign of reproduction kernel Hilbert spaces came with the beautiful theories and sound results for nonlinear modeling, then moved to neural networks, and subsequently and more recently to attention transformers and self-supervised learning. So this is basically, in very short, my career. So I feel myself very lucky because I really experienced, not only read or heard, I really experienced this evolution, or I would say this revolution, from the linear single layer to nonlinear multi-layer, and from the single models to many models that cooperate, because, I have also worked on diffusion models, on cooperative models. So that's sort of my journey. And that's a little bit ironical because I finished my journey that now I realize that I could summarize in maybe 5 minutes the journey of a professional line that's lasts for a few decades, but that's life.
Yeah, sure. That's very interesting. And it begs the question, you currently, after this journey, you are an inspiration to many. So looking back, did you have as an inspiration, somebody who cheered you on as you maybe developed or chose those particular topics for your postgraduate studies at that time?
That the inspiration came from Norbert Wiener's book. That's it. Yeah. Yeah, that was very powerful. Yeah. And also, life is always strange and likes to make games. Sometimes life can be quite playful. So a few years ago, that I was honored and lucky, I think, to receive the Norbert Wiener Award. So at the time that I was receiving the thing, this moment, almost 40 years ago, that it was Norbert Wiener's book that really changed my career, I felt very strange. But
Out of place, maybe?
No. After so many years, I learned my place. Yeah, I belong to this. Yeah, and I never regretted that. Yeah, it's very fascinating field. Yes.
Thank you, Sergios, for that concise summary of your journey. Really interesting to learn your way through ever since you were young and how you've developed that interest. So if we move a bit into some of your insight into the technical work that you've done and what you've alluded to in your introduction, your work in pattern recognition has been widely recognized around the world. How do you see the foundational principles of pattern recognition aligning with the current applications of AI and ML for signal processing?
Yeah, that's sort of very interesting question. And many people ask similar questions, especially younger people, when they want to place signal processing within the general sort of jargon of machine learning and AI. So in order to answer your question, I'm promised that I'm going to answer. I would like to clarify first what these terms mean. Because these days, the terms artificial intelligence, AI, and machine learning are interchangeably used by journalists and also by the non-specialist public. But since here we're not that, we're a little bit of a specialist, I think we should make sure what we mean by that, right? So the way I see this, for example, artificial intelligence is an umbrella that covers various techniques which comprise a discipline whose goal is to develop theories and computational models and build machines that mimic the intelligence activity or the intelligent activity of our human brain. Or if I would put it in a different way to state it differently, basically artificial intelligence is the field whose goal is to build machines that possess human-like intelligence. So AI is a very general term. Now, machine learning is a subtopic of artificial intelligence, where the goal is to deal with data, which is low-level information, and extract knowledge from this low-level information, which in the jargon, we call them data or signals. Signals are data. But, there are other techniques. Reinforcement learning is not part of machine learning. And also more classical techniques based on rule-based systems, knowledge-based systems, or rule-based systems by exploiting formal languages. Also, it's a different type of artificial intelligence. So machine learning is just a specific part where they extract knowledge from low-level information and it makes predictions. That's very interesting, I think, because these days, with the advent of large language models, there is a big discussion among philosophers and linguists and scientists whether reasoning can be extracted and learned from data, from low-level information, instead of providing reasoning via rule-based. Because we know that these large language models, ChatGPT and the related platforms, they have acquired some means of reasoning. Not very successful yet, but possibly in the future is going to be more successful. So it seems, or maybe in the future, the distinction between machine learning and rule-based reasoning of AI, so the distinction may not be as rigid as we think. So coming back, what is pattern recognition? Well, pattern recognition is one of the pillars of machine learning, where the goal is to predict the discrete classes or the discrete groups in which data belong. For example, we may have images of cats, dogs, and in pattern recognition, the system decides on a discrete label, this is cat, this is dog, all right? So that's one part of machine learning. The other pillar is what we call regression. The difference is that the target now is not discrete, but is continuous. And classical signal processing tasks like filtering, smoothing, they belong to, in general, to this regression task. Therefore, these two, pattern recognition and regression, which are the two pillars of machine learning, actually lie at the very heart of signal processing. It will be more clear in a minute. So I would like to put that in a sort of more philosophical jargon, if I may, and say that machine learning, or this aspect of machine learning, lies at the existential roots of signal processing. So what is signal processing after all? Signal processing is just we process at the first level signals. And what are signals? They are data which are either sensed from nature or they are data which are produced by man-made devices, or they are data which are generated by the computer. And at the first phase, we have to clean this data in the sense we have to remove unwanted information, noise, interference, and from the useful information. But once we do that, that's the processing stage. In the signal processing, and that we do that for many decades, we have to analyze and extract knowledge for these signals. So typical examples are the speech recognition, the audio recognition, which has been at the very heart of signal processing for many decades, since the 1960s, even before the digital signal processing appears. Digital signal processing comes later on, middle 60s and later on. Or image processing with image analysis and image understanding, So what are these? They're signal processing tasks. But what they do, they evolve pattern recognition, and they evolve regression through the filtering. What we say machine learning, and it's basically heavily involved and related to what we've been doing in signal processing for many decades. Look, I'm not going as far as to say that signal processing is exactly machine learning and vice versa. No, that's a bit too far. What I'm saying is that signal processing has a core set of topics and problems which is shared heavily by machine learning. Now, what has changed? Well, what has changed is that we have now, due to the advances in machine learning, we have new tools at our hands. So instead of linear and single layer models, we have nonlinear multi-layer model. Also, instead of handcrafted features, and what is a features? Feature is sort of a representation, an information-rich representation of my input data, so that in order to extract knowledge, I have to make a very compact representation so that to be able to work with that. I mean, nature and in our brain, this is also what is happening. Now, instead of these handcrafted features, we have what we call end-to-end learning. So we learn the features, we learn the representations together and combine in a common optimization task with the prediction models. All right. So also we have new application areas which we didn't have a few decades before. For example, autonomous car. That's a very new application for signal processing, for LiDAR, radar signal processing, image processing, and these things. So basically, machine learning and pattern recognition, or this type of machine learning, we've been doing that, and this is the main goal of signal processing. The only thing changed is we have now more powerful techniques to deal with. So the goals have not changed. Things are there, and that's natural. I mean, in all sciences, there is an evolution, there is a progression, and novel techniques, novel models, novel theories come to supersede or complement the previous. So I cannot see, any big fuss on that. Signal processing is here. Signal processing is still, kicking alive. And these new techniques that started from machine learning community, which is, again, it's a community that came out from control, statistics, computer science, signal processing. It formed a new community, but these new tools can readily apply to signal processing and, of course, give new life in that. The goals are the same. Area is there. More tools are available, which make life more beautiful, a professional life more beautiful in the sense, it's more exciting.
Yeah. And actually that builds that now the platform to talk about particular projects, which is my next question, because we've spoken mostly from a philosophical point of view. Will you discuss with us a specific project where machine learning significantly improved outcomes of signal processing? And these you can give from maybe the work that you engaged in terms of the projects you've done.
You see, it's difficult to think of any scientific discipline that has not benefited or significantly benefited from machine learning. That's why these days we talk about a paradigm shift. Okay, so the changes now are not only of an incremental nature. The changes are much more substantial, and by using, what the philosopher Kuhn said, that's a paradigm shift, because the changes, they don't only give us better results, but there are also some qualitatively differences compared to the oldest techniques. We have to be fair. And now, reading newspapers and, in television, some interviews or talk about machine learning and the advances in machine learning and advances in AI, that's fine. But what is happening in technology today is not only due to advances in machine learning. This happened because machine learning had access to big data, all right? And also what happens in technology today is because of advances in computer science. We have a cloud, we have efficient algorithms for searching, for storing, and also we have powerful processors. without this, there won't be all these magic and beautiful results. Also, this would not be possible if we didn't have the internet and the advances in computer networks. Because in order to get all this big data and inform this big data and get data from the internet, you need advances in communications and internet technology, all that stuff. So what we call advances in machine learning that has really changed the technology and also the research, we should be more careful and we should really give credit to other communities. Now, with respect to signal processing, honestly, it's very difficult to pick just a single discipline or a single topic. The adoption of novel and recent machine learning techniques or machine learning models make a difference. But just for the sake of discussion, I would take two examples. One is speech recognition and audio recognition and in general, natural language processing. I mean, the large language models have really changed. Not only the results are different, but, for the first time, we have these machines that can generate speech, they can generate data, right, in such an impressive way. The other also field, I would bring it as an example, is the image processing and image analysis, image synthesis, image generation. And why I pick up these two areas, it's just because these two areas have spread well beyond the small borders of science and technology. I mean, don't forget that one of the major goals of science, at least in the way that forefathers of the scientific revolution, envisioned, is that the results that affect the non-specially public can really feel that. And these are impressive results, and especially in their multimodal implementation. What I mean in the multimodal representation, in the sense that you have a machine that, accepts text, speech, image, video, so all them middle together. The results or the effect of machine learning techniques, they're just amazing. And what we're experiencing now, it is unprecedented. It's just a paradigm shift. But this is also happening in every area, but it's sort of more disguised, hidden in the equations and the jargon and thing. But every area has been revolutionized, and of course, not only science, but also society. But I may make some comments later on. Nothing is the way it used to be, sort of, let's say 10 years ago, or maybe less. After 2010, things have really, there is a leap. Yeah. That's why we talk about the fourth industrial revolution, because that's not only we have new results and new machines, but there is a qualitative difference of what we have today compared to what we had before. It was not just better; they are qualitative different.
Thank you. That is quite an interesting perspective, that you cannot solely put your finger on something, one project, but the whole example of speech recognition is well perfectly understood. And then that puts a context for what is the role of traditional signal processing for this time and age. Is it out of place? Is it still that it forms the foundation of these new techniques such as machine learning?
Well, I will start it sort of in a provocative way. It's the same thing what happens with all the people in the societies. Are they redundant or they are useful? So I will come back. Let's say now what we mean by traditional signal processing. Because as I said before, the problems are basically the same, enriched with more applications. So basically it's data processing and extraction, knowledge extraction. That's the field, and then make prediction. That's the thing, all right? From the same time of signals that we've been audio, speech, ECGs, EEGs, radar signals, just how one could define or describe definitions are risky things. We can define things in mathematics, but every other definition is very risky in life and in science, unless it's mathematically defined. So let's describe what we call traditional signal processing. Traditional signal processing comprises, first of all, linear models or nonlinear models, but single layer models. So that's one, I think, of the characteristics of what we call traditional signal processing. The second characteristic of what we call traditional signal processing is that it used to be model-based, in the sense that for every subtask, for every particular problem, we had to develop a specific model that worked for this particular data and optimize with respect to this data. And we used to develop handcrafted features. And what are the features? As I said, representations, okay? So for images, we had this type of features. For speech, we had time frequency, we had blah, blah, blah. The knowledge representation was sort of handcrafted by the user and defined also by the specific application. And then, of course, a big thing for the traditional signal processing was the transformations, okay? Fourier transform, wavelet transform, discrete cosine transform, sine transform, all that of transforms that, the signal processing was rich in proposing transform. What is a transform? Well, a transform basically, it's an attempt to take your raw data and represent them in a compact way so that you can deal with the information that resides in the data in easier way. So the transformations which we used, they were taken from mathematics, but they were fixed. They were not data adapted. So I think I would say that these are the three characteristics that we call traditional signal processing. What has changed now? Well, we have multi-layer models, and that's very powerful model. Okay, this is deep networks. And of course, this is because we're trying to mimic the way knowledge is represented layer by layer, representation after representation, from low level to high level semantics in our brain. So this is what we do with multi-layer. So that came from the machine learning. But at the same time, because of this, these models are very general, all right, we can represent a diverse range of data. And also, we have gone beyond the model-based handcrafted features, because now we can have what we say end-to-end optimization. So we start as input to our system with raw data, and then we get the semantic information or the representation, and then we get the model that makes the prediction, and we optimize that throughout. So this is a different, also a change. Finally, we have moved slowly, and without maybe understudied, from fixed transformations to data adaptive transformations. What is a transformation? You start from your data and you go into another space, right? The Fourier space or the wavelet space, where you can exploit certain properties of your signal. For example, if you go into DCT and you get the DCT of images, then this is sparse because most of the coefficients are zero, and therefore you can exploit this property in the new domain. But now you can do that by the encoders. When we call, what is an encoder? An encoder is a transformation. It gets an input and it gives an output, and the output is what? It contains a more compact, information-rich representation of your data. So now we have more and more data adaptive transformation. Now, are the old techniques for the dustbin? Of course not. First of all, you get simple linear models. First of all, they are very useful from a pedagogic point of view. You cannot just go to a newcomer and start, playing with transformers and large language models to solve problems. They're not going to understand anything. The kids have to understand the problem and play with the problem. So from a pedagogic point of view, the classical signal processing is there, transformations. And also, we gain something, we lose something. The traditional signal processing, these simple and theoretically beautiful, tractable techniques, they were interpretable because of their simplicity. You could understand why your model predicts A or predicts B. Now in these new models, because they're huge and very general models, we have lost interpretability. They gave you a result because they have been trained, but you don't understand why you get this result. All right. So of course there is research on that. There is a lot of research and an effort to make interpretable or at least more interpretable. So you see that classical signal processing is here. Also, let us not be sort of overkilling guys. Still, industry, you have some problems that can be solved with classical signal processing. You don't always have to train things with massive data. You don't have to overkill. So definitely, signal processing, all these techniques are here, and classical techniques can also help us in trying to develop interpretable models by more carefully looking at them. Maybe younger professors are going to attend this lecture. That's a sort of an advice. It says that we should, during the courses, especially via the graduate, but sometimes also in the postgraduate courses, we have to pay a lot of attention to the classical signal processing, to the classical techniques. I'll give you an example. I mean, we have computers now that they can add numbers, they can multiply numbers, they can integrate, they can differentiate. This doesn't mean that our students must all understand what an addition is, what a multiplication is, what an integration is, and they have to play with their hands first in order to understand what this means. And by doing that, then they are then more able to understand the more complex models. And I'm going to finish this very interesting question by taking an analog. As a hobby, I'm very much into sort of painting. I know many artists, so they have a similar problem. Artists now use in a modern way. They are modernists. However, you know what they say? That in order to know how to paint in a modern way, first of all, you will be able to paint in a classical way. So this we have to keep in mind. We cannot throw the old stuff away. Coming back from the beginning to the beginning, we cannot throw old people from the society out because they are not active, because they have something. They have their wisdom, they have the wisdom of life. They can interpret things better, right? And then also at the same time use the novel tools.
Very well answered. You allude to which or traditional signal processing be more complementary to machine learning and more advanced techniques.
I don't like to use the words complementary or competitive. That's an evolution process. Science is evolutionary, like the civilization. Paintings and art that has been produced in the caves still means something that is very important to the civilization. It's not better, it's not worse. This similar things applies to science. It's just an evolution of techniques, and in order to start and being able to handle the new tools, you have to be familiar with the older tools, with the roots.
And maybe let's take it a little back when you mentioned that when you talk about the advancements there are in signal processing, we need to give credit where there is due. For example, on big data, on the network's operations. That builds context for my next question. And I want to know what is the place of collaboration in achieving all these innovations that we have? And is interdisciplinary work something that you had experience over your extensive career?
I understand that when you say collaboration, it's not collaboration with other people, but collaboration in the sense of interdisciplinary, collaborating with people from different disciplines. Do I understand well? That's the main...
Yeah, that's the whole aspect, yeah.
Yeah, look, interdisciplinarity is a trait these days that springs from the needs of today's technology. Today's technology is complex because the needs of our society are much more complex, and the demands from our society are more complex. I mean, the living standards and also customs and everything, the demands of a society cannot be compared with the societies of 100 or 200 and 300 years ago. And this is also, to a large extent, is due to technology. I will give two symbolic examples of what it means interdisciplinary research. Who are the recipients of the Physics Nobel Prize this year? Jeffrey Hinton and John Hopfield. All right? And they got the Nobel Prize of Physics because of their work on machine learning, of their networks. Who was one of the recipients for the Nobel Prize of Chemistry? Dennis Hazapi. All right? Again, he's not a chemist. So what it means, I mean, the Academy, the Swedish Academy, they decide the Nobel Prize, they realized how important these networks and the computational models are for physics, chemistry, and I'm pretty sure that similar comments can apply to other sciences like biology, economy theory, and all that stuff. So now there are two aspects of what we mean and why interdisciplinary research is very important these days. One aspect is that these models that we use, large language models, transformers, and also in general, multi-layer or deep networks, convolutional neural networks or recurrent neural networks, first of all, they have very high, compact, information-rich properties for representing data. Okay, they can extract the very basic underlying structure of the data, and they can encode it in a very compact, information-rich representations of the outputs. But at the same time, these models, because they are complex, large models, they have a modeling generality. So now the same model can be used in biology, can be used in computers, can be used in control, can be used in signal processing. So therefore, the use of the sort of more or less the same models in different communities can only be of benefit if these communities can exchange experience. Very often when, I want to apply and develop a model based on deep networks, many times I have to read biology or papers or finance papers because they have used the same models, so I can gain. And I guess these people can also gain from me. When I say me, I mean from a signal processing guy or a lady. So that's one type of how interdisciplinary springs from today's methods. However, there is something which is even more important. And this importance comes from the fact that technology today is much more complex in the sense that it has to meet the needs and demands of more complex societies. And this may sound sort of either complicated or may sound impressive or whatever. I'll give you an example. Let's go the power generation. What was power generation as a topic, as a scientific discipline 2 decades, or let's say three decades ago, maybe 2 decades ago, was sort of part of electrical engineering departments. And what was the goal of the power engineers? Just to develop machines that, they could produce electricity in a very efficient way. And as a matter of fact, these guys, they were a bit looked down from sort of a more modern scientists like computer science and things, and even signal processes, because that was too classical stuff. And also they had some to deal with the distribution. But what is the distribution? You have the lines and you have some power stations. But here, what do we have today? We have power grids. Why? Because the needs now, we have a climate change. So we have to combine generation from different sources, sun, wind, of course, hydroelectric, all different types. But also we have the distribution, because we have to be very careful and sensitive on how we consume energy. And therefore, now the distribution network, it's much more complicated. And that's why we call them smart grids. And so you need power engineers, you need computer scientists, the algorithms to run. You need communication computer engineers because, that's a whole network. You need signal processes with sensors and devices. And of course, you need machine learning guys because you have to analyze all this abundance of data. So that's, you see, this field now, it's by itself defined as interdisciplinary. Another example, of course, I don't have time, it's autonomous cars. There's so many different disciplines involved in order to be able to make an autonomous car or sort of autonomous vehicles in general. The same could apply with biology. You have this DNA sequences and things. So a classical biologist who just only, is in the lab and tries to find, all this chemical stuff, that's not enough. They have to cooperate with computer scientists, and there's also signal processes that they're looking at the sequencing. Things are different. Everything has changed. And therefore, this is something that the universities have to pay in organizing their curricula. We always had, especially in the United States and in some universities in Europe, the students could take some philosophy courses and some history courses. But here, besides that, these are also very important in a society which there is a danger of becoming too technological. These topics of philosophy and ethics, have to be priority. But besides that, the students have to learn more things, biology, a bit of economics. Why? Because when they go to the industry, they have to cooperate with people because what they are going to produce is the result of many different, so they have to understand the language of each other. So interdisciplinary is a trait of today's science, is a trait of today's technology. And of course, science and technology is not independent on what is happening in societies and in the world. The world is much more interdependent now than it used to be. Everything is interrelated. This makes things more excited and makes people more open-minded because they learn each other. They come, every community has a different culture. That's beautiful, you see. That's beautiful.
Very interesting perspectives. And wonderful to hear that indeed it is more collaborative work that steers the field and indeed the whole technology in the right direction. Now, moving on, as you have been editor-in-chief of the IEEE Transactions and Signal Processing. Even from your story earlier on, you must have seen a lot of these advancements. And what I'd like to know is, looking or peeking into the future, what do you think is going to be the next big innovation from all of these AI and ML?
Well, I'm old enough and I want to believe that I'm a little bit wise enough so that not to make predictions, because this is what I learned in life in general, right? But I will be more now a bit more philosophical in the sense that, you see, novelty is by itself not predictable. Because what is novel? Novel is something that is qualitatively different from what it was before. Otherwise, we call it a small advancement or an improvement. When we talk about real novelty, cannot be predicted. But also what we cannot predict from novel ideas are the implications of the novel ideas. I mean, who could imagine or go back and read in the papers for the first paper that was published on attention transformers? That was something that was, focused on natural language processing in the sense of a text, all right? To produce text and maybe to use it for classification, for sentiment analysis and all that. But now, look, large language models and transformers are used everywhere, all right? So nobody could predict, even the people, the colleagues that propose that model, predict what will happen. And the same maybe happened, with the diffusion models in 2015 when the first paper appeared. by exploiting certain ideas from theoretical or statistical physics, that remained obscure, solving a specific theoretical problem. And now diffusion model is just going, like crazy. And that's not only after 10 years or 20 years. It's after 2 or 3 years. So predictions in the times when things are changing very fast and when technology is really changing not only by small leaps of improvement, but also generated products and platforms that have a qualitatively different performance and behavior with respect to the previous era. I think I cannot predict, and I must not predict, and I have to say that sometimes I'm very suspicious of people who come, especially the television, and they make, sort of deterministic predictions with a sort of authoritative way. That's I think this is completely funny. So I won't make any special predictions, but I could make some guesses. I think for the next years, definitely large language models and generative models will be around and will be thriving. I have a feeling that there will be a comeback to the recurrent neural networks. It was thought after 2017 they were superseded by the transformers. They are coming back, and it seems that they may give some comparable performance. But the only thing that can make a prediction is that the times ahead are going to be very interesting from a scientific point of view. There are going to be sort of significant happening with new ideas for a few years ahead. I don't know how far that will go and if it settles after a few years. But for the next 4, 5, 6 years, I feel that there are going to be plenty of ideas, and I really regret that I'm old enough so I won't be able to be really part of this activity to enjoy it.
Let's reflect back and from the various comments around the various areas that you've given us, I would like to know from this extensive career and satisfaction that you found in this space of signal processing, when you look back, what is that most rewarding aspect of working on this field?
Oh, that's a very interesting question. And you see that this also, comes with some more general thoughts. Once, get old, you try to remember from everything that you did in life was worth it. And it was worth it to keep it, and what it was useless and not worth it. And you try to put it in the dustbin by just trying to forget it. When I go back to my career, I try to keep what is really worth it, keep it in my mentoring to younger people. I think that was really something that not only I joined, but something that it was worth doing it. And I think it was a significant part of my professional as well as my personal life. And also my teaching. Younger people and trying, not always being very successful, but trying to inspire them and raise sort of dreams and goals in their intellect so that to get involved with signal processing and with science, which, subsequently would really make them to delve into uncovering the secrets of signal processing and secrets of science and push the barriers even further. I consider these as the most important things of my career. And I have to say that in a number of times, I have been quite successful, and I don't take it, literally, and I'm going to explain what I mean successful. I think the main goal of any teacher is to help students to become better scientists than him or her. So I was lucky in my career to see a number of my students to have become later on better scientists than me. And that's very rewarding. And I keep that in life because that's continuation of life. Yeah.
Thank you. That is very inspiring to listen to. And while I'm at students, I have a bonus question as we wind down. And this is about your recent course, a machine learning lecture series that has been published on the IEEE Resource Center. It is very in-depth, quite long. Could you give a short summary for our listeners so that they can go and check out the course on the SPS Resource Center?
Yeah, thank you. Yes, the lectures is sort of the outcome of many decades of teaching machine learning related courses. And also they are complementary to my second edition and also third edition, of which is going to be published sort of very soon, of my book, Machine Learning. It's just complementary. You don't need the book in order to follow the lectures. Now, the lectures comprise 5 parts. In the first part, deal with the general concepts of statistical parameter estimation and the basic definitions of regression, regularization, bias variance, trade-off, and cross-validation, and all is very basic stuff that everybody that has to enter and learn both signal processing and machine learning, that's a common core, has to follow. And the first part is mainly focused on regression. The second part is mainly focused on classification, and there it deals with, again, very classical knowledge that it's really a must to everybody that tries to learn machine learning. Basic decision-based theory for classification and, minimum distance classifiers, Fisher's discriminant ratios, all the basic decision trees. So that's the very classical stuff that also they form the pillar of machine learning. Then part 3 deals with learning in reproducing kernel hidden spaces, support vector massage, support vector regression, and all that stuff. And part 4 deals with deep networks. So it starts from the very beginning, the perceptron rule, feed-forward neural networks, and then moves to deep networks, convolution neural networks, recurrent neural networks, GANs, generative adversarial networks, adversarial learning, also the attention mechanisms. It covers all the basic stuff for deep networks. And the fifth, part 5, is Bayesian learning. EM algorithm, variational versions of the EM algorithm, which sort of a little bit more advanced topics for those who want to learn more on the Bayesian learning, also for those who are interested more for statistical signal and signal processing. Of course, the book is not intended for people or for students who are interested in just sort of black box courses. For example, just use this platform, use program, you put in data and you get out results. No, the lectures try to unveil the physical reasoning which are associated with the basic equations, and without it is not delving into deep equations, but just very little for definitions. But I spent quite a lot of time in explaining the whys and hows and the physical reasoning, so that the newcomer in the field can really grasp the basics on which he or she can later on step to read more different techniques. So this is what lectures are about. And I hope that soon I'm going to enrich it with another part that will involve self-supervised learning, diffusion models, and transformers in a more detail, which are parts of the new edition of my, of the third edition of my book.
Wonderful, Sergios. Thank you for that concise summary of the course. It has been wonderful hosting you, Sergios. Your contributions have not only really advanced this field, but has also inspired countless professionals and researchers around the world. It was truly an honor to have you for this podcast, and we look forward to many more conversations maybe in our next episodes.
Thank you very much, Dennis, and it was really an honor and a pleasure for me to be with you. And thank you very much and for the interesting questions.
Thank you. And to our listeners, we hope that this conversation has offered you valuable perspectives on the ever-evolving role of AI and ML in shaping the future of signal processing. If you'd like to explore more, we highly encourage you to check Professor Theodoridis' course on a machine learning series that's available now on SPS Signal Processing Center. We thank you for tuning in and hope to have you on our next episodes. And until next time, goodbye.